My name is Tim Verhey. I'm Executive Vice President at Walters. I've been here for 25 years full-time, and my role is engineering and operations. The 160 front tower is a gem on the skyline of Toronto. It's one of the most shapely buildings that's been built in the last 20 years and will definitely make its mark on the skyline. It's a 47-story, high-end commercial space that will house the Teachers' Pension Fund, as well as be the new head office for the Toronto Dominion Bank. As you get into mid-rise, which we would call from 20 to 35 stories, steel is and remains a very viable material, but ever more so as you get taller than 35 or 40 stories. And that's because the competing materials are concrete, and concrete requires more area to create the same amount of strength. So on a high-rise building, you use ever more floor plate for columns, and that doesn't work with the developer's pro forma. They want to maximize floor space. They want to maximize column-free areas for their tenants. So in the commercial space, typically they're constructed of structural steel, but they are hybrid in the sense that the central core of these towers is reinforced concrete. It contains a lot of steel, it contains a lot of rebar, but the real strength of steel is for the perimeter columns. Keep them nice and compact, allows you to get the large column-free spaces, and you can get the height. There are some hidden features which pose significant design challenges. And if you look at the building, there are inlet features. So on the two faces of the building, it looks like a little slot in the side of the building, and there's one on each side at the mid-height of the building, and then there's another one closer up to the top of the building. Those are inlet features. The challenge with the inlet features is the main columns had to index inwards and then back out again. So if you can visualize these very large columns at the perimeter of the building, and if you jog them, you introduce significant lateral forces. Concrete tends to settle and shrink, and then the structural steel, it's a linearly elastic material. It will compress under load linearly, but they happen at different rates. So the joints and the details had to accommodate very high forces, but also movement. And we came up with a really clever concept utilizing a simple pin. So we have simple pin joints to deal with these massive loads through this complex interplay of steel shortening and concrete creep on the core. And it was, at the end of the day, very simple, but it took a lot of brain power between ourselves and RJC to figure out how to do that. Simplicity is often the best, but often simplicity is elusive. It takes a while to get there.